I am a PhD student in the Department of Chemistry at the University of Florida, and I work in Audrey and Royberg's lab. And so we're computational chemistry, and something you've probably all heard of is the Schrodinger Equation, which basically outputs the energy as its eigenvalue, and then the wave function, which describes how the system will behave. So if solved, it can tell you just, a lot about your system, but the more complex your system gets, the more complicated it is and unattainable an exact solution is. So in CompChem, we use computer-based methods to approximate these solutions, and obviously these methods are very successful. They're used all the time. And they give you a lot of chemical insight, but they can be quite costly and limiting depending on the size of your system and the accuracy that you want to achieve. So a cornerstone in the field is bridging this gap, but it's not trivial because most of these methods scale to system size. So we want to be in the low cost range while obtaining really high accuracy. And so our solution to bridging this gap is through our method ANAKIN-ME, which is Accurate Neural Network Engine for Molecular Energies. And we want to train a network to become what we call QM Jedi Master. And we want to be able to obtain those energy values quickly at high accuracy level of theory. So ANI fits into this high accuracy, low cost region. And ANI is a transferable deep learning neural network potential, and it predicts the energies and forces of small drug-like molecules. And our models are trained to DFT, which is in the higher cost region, but also very high accuracy. And currently we have 4 published models to date. The ANI-1 series allows for computation of carbon, hydrogen, nitrogen, and oxygen containing molecules, and ANI-2X added the sulfur, fluorine, and chlorine. And then we also have a network called 1CCX, which was transfer learning, adding couple cluster data. So our code is called TorchANI, and it is a Pytorch implementation. It's open source and available on GitHub. Our original implementation was called NeuroChem, and it was coded in C++. And this was nice and it was fast, but it was not very user-friendly. And it was much harder to make modifications, which the second generation of the ANI research students, that's what we all do. We're trying to modify it and make quick changes. I gave it a thumbs up too because I felt like the Ghostbuster sign on top of NeuroChem was a little aggressive, but NeuroChem was really good, but it's just, we don't use it anymore. And this is just a rough outline of just ANI through the ages of the 4 publications we have and what it went into them. So our original one was ANI-1, and we trained it on way too many data points. And it was just your simple basic training of a neural network. Our ANI-1X and 2X were both trained with using the active learning method. And then obviously 1CCX was transfer learned. And in terms of application, how we use ANI and how people in other fields use it, but ANI outputs energy values, and it also outputs forces because those are, the gradient of those energy values. And we've been able to apply these to get torsional profiles of different systems and in molecular dynamics. Also recently in 2020, the Leahy group published this, and we were not involved in this publication, but they took ANI and proved that it outperformed 4 of these commonly used force fields in predicting the torsional potential energy scans for this large data set to the left. And if you look at the violin plot here, it shows that both ANI2X and ANI1CCX have lower root mean squared deviations and standard deviations than the other methods. And then when they looked at just one structure, torsional scan, and ANI2X and 1X basically correlated with couple cluster much more than all the other ones did. And as I pointed out earlier, it doesn't matter really how accurate we are. It more matters what, speed we are able to do these computations. So the paper did claim that we are 7 times faster than CGen FF, which I don't really work with force fields that often. So like the hierarchy in terms of what's the best is not really something I know, but the paper did say it was like one of the higher accuracy force fields. ANI works, but how does it work? What's its architecture? So our data sets consist of only species, coordinates, energies, and forces if you're training to forces. And our input to our networks is a molecular representation called an AEV, which stands for Atomic Environment Vector, which I'll go into more detail in a minute about those. But it is a coordinate-based representation. And each atom type that our network allows has its own network. So for ANI1X, we had a hydrogen atom network, carbon, nitrogen, oxygen. And each network outputs what we call an atomic energy, which is a non-physical value. It has, no physical meaning, except that it is part of the total energy, and that our total energy is simply a summation of these values. Also something I find important to always mention is that our network actually outputs small near zero values that we call raw atomic energies. And we apply an energy shifter to each of these to correct them to the molecular values, which I'll also go into detail of why. So first let's look at the AEVs. The inputs to our network, like I said, all have to be fixed size. So we do this by having these AEVs, and we have an AEV for every atom in that system. Because we have an AEV for every atom, this is our bottleneck. This is what takes the longest time, is computing these AEVs. And we look at about a 5 angstrom radius around the atom and create a vector of the radial and angular information in regard to that atom. So if you're looking at a carbon atom, and in that 5 angstrom radius, you have some hydrogen atoms or, another carbon, that information will be, in the distance information will be in this vector, as well as the 3-dimensional information. And these are fed into basically, if you're looking at a carbon AEV, that's obviously going to be the input for the carbon neural network. And one problem we always run into is what I was talking about with how this is our bottleneck, is that if we want to add more available atom types, the size of these AEVs grows exponentially. So just by adding 3 new atom types, it went from 384 to 1,008 quantities. And so they require more memory and they slow things down. So we currently don't have an exact solution to this issue, but we do have a student that's the project he's working on, trying to decrease the sizes of these inputs. So one thing I always like to talk about are the energy shifters. A lot of people leave these values out, but I work with them a lot, so they're important to me. So in the published ANIs, they utilize what are called SAEs, and these are atomic constants that will come from just basically a linear regression of your training data. So that means that they're model dependent. For every new training set that you have, you'll have different values for each atom type. And so, we do this because we want to subtract the baseline from the total energy and shift it to numbers that are small and let the network work on these small numbers. And this is important because suppose you didn't do this and you're training the carbon network to these like, 38 Hartree values, and then you're training the hydrogen network to these like 0.5 Hartree values, then basically the model is going to learn that it doesn't really matter what value the hydrogen is because it's negligible to the carbon, right? So we have to subtract this baseline. And the SAEs, they bring everything down to a standard so that they'll share similar values. And part of my work has been changing this up a bit. I don't want to do a linear regression of the training set every time, first off, but also in my work, I want to obtain pure interaction energies. And so that average doesn't, account for that. So I use what I call like the ground state atomic energies that are computed with the reference level of theory that we're using for the training set. And so also most ANI users now are using what I call the GSAEs. So in future publications, you won't see SAE anymore, probably the GSAE. And just as a midpoint, in the spirit of SciPy, I want to shout out all the open source packages that we use to do all of this for TorchANI. So I just want to first off show you how quickly ANI can compute a substantial data set, and then also show you our optimizer because that is really useful. So in TorchANI, we also have like a data set loader so that you don't have to modify your own data. It can go into all of the TorchANI functions. And so I'm not going to go through all that, but that's what that's doing. And in our data set that we're looking at currently, we have about 158K conformers. And in order to load this data set, it took about like 7 seconds. Yeah, we have to set our device, and here we're running on a GPU. TorchANI can run on CPU as well, but obviously it goes a lot faster on GPU. So we're looking at a GP100 at the moment. And so I want to show off the speed, but let's just look at the ones that have more atoms, like the larger molecules. And so I just set it to the molecules with more than 50 atoms. So our average number of atoms in a conformer is 73, but you can see here that there are some a bit larger ones in the 300 range. And we have about 11,000 conformers in what I'm about to run. So we load our model here. And sorry, I'm not actually doing it now because I'm scared to like mess everything up. But it only takes 6.2 seconds to get all of the energy values from that data set. And if we want to run it on the whole like 158K structure data set, it takes 17 seconds, which is substantially fast. And if you imagine too running all of these structures on DFT or something, it'll, who knows how long it would take, especially with like a 300 atom structure. So we also have the Ase Interface, which is how we optimize structures, and you can set TorchANI as the calculator. And I'm not going to go through all of this, but this is just our optimization, and it only took 7 seconds as well to optimize the structure, which compared to DFT is very fast. And so also we're able to visualize these optimizations to see how ANI is, moving this molecule and computing these values. That's just always fun to watch. And you can see that it's basically able to take into account like these hydrogen bonds and how, this structure should move in order to get to its lowest minimum energy structure. Okay, and finally, just at the end, I want to talk about the work that I actually do instead of just talking about general ANI, and that is ANI-AIM. And it's basically the development of a new type of atom and molecules partition. So I care about just the atoms, not technically like the whole molecule. I do care, but I just don't often look at that information. And so ANI originally fits to the total energy. When we train our network, we only care about the summation of the atomic energies. And for this approach, we'll add this electrostatic part, just a Coulomb energy function, so that the model will be parameterized to fit for atomic energies and atomic charges. And this is done in a lot of different networks. Like everyone has their own method to compute electrostatics, but for us, we want it to be solely based on the energy. We don't want to train to specific charges. We want it to be like each charge to basically be just a function of that energy. And the key is that like we don't want to assume anything about the relationship between the energy and the charge values, except that we're predicting the pure interaction energies, and these correspond with the charge state that the network is actually predicting. So I wanted to start this project by just seeing what ANI could do. I didn't want it to give it any charge data, any information, except like the only constraint was charge neutrality, so that like it would, sum up to the charge of the system that you're looking at. And I obviously ran into a lot of issues with this. That doesn't work. It needs to know more, obviously. Like you can't just expect the network to, know that information. But I just wanted to see, and the biggest and most significant one was that there wasn't a way to stop these charge values from being model dependent. They had nothing to grasp onto, no information they needed. So you would train one network and you'd look at a water molecule and the charges that are associated with each atom, and you were super happy. You're like, yes, the oxygen charge looks good, the hydrogen charge looks good. And then you retrain, look at it again, and you'd have negative charge hydrogens, which for the non-chemist out there, that's not good. Yeah, so I still want to have the same goal that I have, which is the energy and charge values. I want them to directly correspond with each other. I don't want to train to some energy type and then some charge type. And so we needed something that had the same taste or flavor as the GSAEs for the atoms. I want, basically a GSAE for the charges. So yeah, shout out to OpenFF Toolkit, because by using their software, I was able to implement a way to predict AM1 BCC charges, which are just good, your charges, of the structure. And I'm using these as initial charges. So instead of directly training to these values, I'm predicting the change in charge as kind of like we predict the raw atomic energies and add back the baseline. These will be unique baselines for the system. So we compute the charges for each system and then add whatever the network predicts as a change. And I've just recently implemented this. I don't have many results on this yet, but like a couple weeks ago, I did train my first network with this method, and the RMSD, like for the validation, was odd. Like it didn't look good. It looked kind of high. It was higher than I wanted. So I need to work on bringing that down before I really start like analyzing more data with it. But this is the state that this project is in now. It doesn't sound like a lot, but it's like been taking a long time with all like the like different theories that I've tried to get the network to just hopefully know charges. And yeah, that's it. So thank you for listening, and thank you SciPy for having me.
Okay, let's see. There is one question that's not a question, but thank you so much for using the Darth Vader no GIF. What other questions do we have? I guess I'll bring it over to you. Others, if you could type your questions into the track questions Lotnik Ballroom on Slack, that would be helpful.
Hey, actually, one of my colleagues a couple of years ago published a paper, like a benchmarking paper, that showed that ANI actually performs closer to the semi-empirical methods, so in terms of like speed and accuracy. So I just want to ask, like, do you have any comments on this, and like, how did you get to the result that showed that it?
I'm sorry, I'm gonna interrupt you. Could you take your mask off? I can't really hear you. Yeah.
Oh, sorry.
No, you're good.
So I'm gonna start from the beginning. A colleague of mine, my group, published a benchmarking paper a couple of years ago that showed that ANI performs around like about the same as semi-empirical methods in terms of like speed and accuracy. So I just want to ask, do you have any comments on this? And how did you get the results it has, like the speed of force fields, but the accuracy of DFT? Because this is not what we saw.
Okay, so were you, I guess I have a lot of questions in terms of like what methods y'all did, but were you looking at energies, forces, do you know?
To be honest, I don't, it's my colleague did, I don't remember it all by heart.
I would like to look at that paper actually, because we have had a lot of times when someone has done that and then we Adrian always wants us to be like, no, that's wrong, and find out why. And we've been able to, so I'm wondering if that's one of them. Yeah. But typically we do much better than semi-empirical, and that's the only comment is that,
I'll be happy to hear. I'll send you
send
a
me the
DM with
paper,
the
I'd
link.
be interested in it.
No problem, thanks.
Yeah, thank you.
Hi, thank you for the talk. I was just wondering, you mentioned active learning, and neural networks usually don't really, offer themselves to active learning. So how did you approach that?
Yeah. I don't have a slide on it. I do somewhere. But basically, we take the system, right? It predicts the energy value for it. And we use something called query by committee, where basically we have a standard deviation of some kind that if it's, higher than a certain, whatever threshold we set for it, it'll send back to Gaussian and it'll recompute this value and we'll do it again and
I think we have time for one more. If computing the 5A local environment for atoms is slow, how is it done?
Can you say that one?
If computing the 5A local environment for atoms is slow, how is it done?
I guess I think they're talking about the AEVs, correct? Okay, so I wish I had the equations to hand. If you look in our paper, our ANI-1 paper, you'll see those equations. But basically, it's there's one cutoff function, and that's applied to obviously the radial and angular part, so that we are only looking at a certain environment, or surrounding this one atom. And we have our radial function, we have our angular function, and this is a bunch of cosine functions. I can't think of them off the top of my head. I wish I had them, but that's basically it. It's just mathematics.